Of all the mechanical waves that occur in nature, the most important in our everyday lives are longitudinal waves in a medium, usually air, called sound waves. The reason is that the human ear is tremendously sensitive and can detect sound waves even of very low intensity. Besides their use in spoken communication, our ears allow us to pick up a myriad of cues about our environment, from the welcome sound of a meal being prepared to the warning sound of an approaching car. Welcome to our Lesson 2 Sound and Hearing. Up to this point, we have described mechanical waves primarily in terms of displacement. However, a description of sound waves in terms of pressure fluctuations is often more appropriate, largely because the ear is primarily sensitive to changes in pressure. In this part, we'll be discussing about sound waves, speed of sound waves, and sound intensity. Section 2.1 Sound Waves. The most general definition of sound is a longitudinal wave in a medium. As you can see, our medium in this figure is air molecules. Longitudinal wave travels along the straight path of the air molecules. The simplest sound waves are sinusoidal waves, which have definite frequency, amplitude, and wavelength. The human ear is sensitive to waves in the frequency range from about 20 to 2000 Hz, called the audible range, but we also use the term sound for familiar waves with frequencies above ultrasonic and below, which is infrasonic, the range of human hearing. The range is 20 below or 20 up. If we say 20 Hz and up, that is an ultrasonic wave. And when we say below 20 Hz, that is infrasonic wave. Sound waves as pressure fluctuations. Sound waves may also be described in terms of variations of pressure at various points. In a sinusoidal sound wave in air, the pressure fluctuates above and below atmospheric pressure in a sinusoidal variation with the same frequency as the motion of the air particles. The human ear in this figure operates by sensing such pressure variations. A sound wave entering the ear canal exerts a fluctuating pressure on one side of the eardrum. The air on the other side of the eardrum, vented to the outside by the eustachian tube, is at atmospheric pressure. The pressure difference on the two sides of the eardrum sets it into motion. Microphones and similar devices also usually sense pressure differences and not displacement. So it is very useful to develop a relationship between these two descriptions. Equation 2.1 represents the maximum pressure fluctuation and is called pressure amplitude, where B is the bulk modulus, K is wave number equals 2 pi over lambda, and A is the displacement amplitude. When wave number K relates into wavelength frequency, a periodic wave is defined as omega equals speed times the K. So, equation 2.2 is given. A medium with a large value of bulk modulus B requires a relatively large pressure amplitude for a given displacement amplitude because large B means a less compressible medium. That is, greater pressure change is required for a given volume change. Learning Activity 2.1 entitled Amplitude of a Sound Wave in Air. In a sinusoidal wave of moderate loudness, the maximum pressure variations are about 3 times 10 to the minus 2 Pascal, above and below atmospheric pressure. Find the corresponding maximum displacement if the frequency is 1000 Hz in air at normal atmospheric pressure and density. The speed of sound is 344 meters per second and the bulk modulus B is 1.42 times 10 to the 5 Pascal. This problem involves the relationship between two ways of describing a sound wave, in terms of displacement and in terms of pressure. The target variable is the displacement amplitude A. We are given the pressure amplitude P max, wave speed, frequency, and bulk modulus B. Equation 2.1 relates the target variable amplitude to P max. We use periodic wave equation omega equals Vk to determine the wave number k from the speed and the angular frequency omega equals 2 pi f. As an execution, from equation 2.2, k is equals to omega over v, or since omega is equals to 2 pi times the frequency, we have 2 pi and a frequency of 1000 hertz, and the speed of the sound is 344 meters per second. When we calculate that, we can get 18.3 rad per meter. Then, from equation 2.1, the maximum displacement amplitude is P max over bulk modulus B times the K. P max is given as 3 times 10 to the minus 2 Pascal, and the bulk modulus P is 1.42 times 10 to the 5 Pascal. Now the K is 18.3 rad per meter. And we can get 1.2 times 10 to the minus 8 meter. Prescription of sound waves. The physical characteristics of a sound wave are directly related to the perception of that sound by a listener. For a given frequency, the greater the pressure amplitude of a sinusoidal wave, the greater the perceived loudness. For example, in this figure, there are small amplitude and large amplitude that represent the perceived loudness of the sound to the receiver or to the listener. A loss of sensitivity at the high frequency end usually happens naturally with age, but can be further aggravated by excessive noise levels. The frequency of a sound wave is the primary factor in determining the pitch of a sound, the quality that let us clarify or classify the sound as high or low. For example, in this figure, we have the high frequency or high pitch and the low frequency or low pitch. When we have a high frequency, we have small wavelengths. So there's a small wavelengths in here. And that represents high frequency. And we have low wavelengths that represents low frequency or low pitch. Two tones produced by different instruments might have the same fundamental frequency and thus the same pitch, but sound different because of different harmonic content. The difference in sound is called tone color or quality or timbre and is often described in subjective terms such as reedy, golden, round, mellow, and tiny. Another factor in determining tone quality is the behavior at the beginning and end of a tone. Unlike the tones made by the musical instruments or the vowels in human speech, noise is a combination of all frequencies. We are now in the section 2.2, Speed of Sound Waves. A sound wave in a bulk fluid causes compression and rarefactions of the fluid, so the restoring force in the above expression must be related to how easy or difficult it is to compress the fluid. It may be gas or liquid. This is precisely what the bulk modulus P of the medium tells us. From this figure, when we open the door, we can imagine the door pushing the air molecules next to it away from their initial positions and into their neighbors. The neighboring molecules in turn push into their neighbors and so on, like a compression traveling along a spring, until the curtain flops out the window. A pulse of compressed air has moved from the door to the curtain. This pulse of compressed air is called a compression. When we close the door pushes some air molecules out of the room. This produces an area of low pressure behind the door. Neighboring molecules then move into it, leaving a zone of lower pressure behind them. We say this zone of lower pressure air is rarefied. Other molecules farther away from the door in turn move to this rarefied region, and a disturbance again travels across the room. This is evidenced by the curtain which flaps inward. This time the disturbance is a rarefaction. Another impression of compression and rarefaction in the air is this figure. The compression here is the air molecules in here, and the rarefaction here is the air molecules in here. Speed of sound in a fluid. The speed of propagation of a longitudinal pulse in a fluid depends only on the bulk modulus B and the density of the medium. Thus, the speed of a longitudinal wave in a fluid is represented by equation 2.3, where speed is equal to the square root of bulk modulus B over the density of the fluid. Equation 2.3 for waves in a pipe also applies to longitudinal waves in a bulk fluid. Thus, the speed of sound waves traveling in air or water is determined by this equation. Speed of sound in a solid. When a longitudinal wave propagates in a solid rod or bar, the situation is somewhat different. Why? Because the rod expands sideways slightly when it is compressed longitudinally, while a fluid in a pipe with constant cross-section cannot move sideways. Thus, the speed of a longitudinal wave in a solid rod is expressed in equation 2.4, where the y is called the Young's modulus. Learning Activity 2.2 entitled Wavelength of Sonar Waves. A ship uses a sonar system in this figure to locate underwater objects. Find the speed of sound waves in water using equation 2.3 and find the wavelength of a 262 Hz wave. The bulk modulus B of water is 2.18 times 10 to the 9 Pascal. The density rho of water is 1 times 10 to the 3 kilogram per meter cube. Our target variable are the speed and the wavelength of the sound in water. In equation 2.3, we use the density of water as 1 times 10 to the 3 kilogram per cubic meter, and the bulk modulus B of water is 2.18 times 10 to the 9 Pascal. Given this speed on the frequency f as 262 Hz, we find the wavelength from V equals frequency times the lambda. Equation 2.3, we simply input the values for the bulk modulus B and the density of the water. We can get the speed of the sound wave as 1,480 meters per second, and by using that speed to get the wavelength of the frequency, to get the wavelength of the sound, we can get it by simply inputting the value of 1,480 meters per second over its frequency, that is 262 Hz, and the total of 5.65 meter. Now, dolphins emit high-frequency sound waves, typically 100,000 Hz, and use these echoes for guidance and for hunting. The corresponding wavelength in water for the dolphins that has a 100,000 Hz is 1.48 centimeter, and this high-frequency sonar system, they can sense objects that are roughly as small as the wavelength of 1.48 centimeter. Ultrasonic imaging, in a medical technique that uses exactly the same physical principle, sound waves of a very high frequency and short wavelength called ultrasound are scanned over the human body, and the echoes from the interior organs are used to create an image. With ultrasound of frequency 5 MHz, that is equals to 5 times 10 to the 6 hertz. The wavelength in water is 0.3 millimeter, and the features as small as this can be discerned in the image. The image in here is a fetus from the womb of a pregnant mother. Ultrasound is used for the study of heart valve action. Ultrasound is more sensitive than the X-rays in distinguishing various kinds of tissues and does not have the radiation hazard associated with X-rays, because X-rays uses gamma rays, and then that has a radiation waves and is hazardous to our tissues when we are exposed frequently in a X-ray room, for example. Speed of sound in a gas. Most of the sound wave that we encounter on a daily basis propagate in air. The speed of sound waves in air is dependent to the pressure of the gas. The greater the pressure applied to a gas to compress it, the more it resists further compression, and hence the greater the bulk modulus. Equation 2.5 represents this, and bulk modulus is equals to this symbol times the pressure. Equation 2.5 is the expression of the bulk modulus of a gas, where PO is the equilibrium pressure of the gas. The quantity gamma is called the ratio of heat capacities and is dimensionless. So the gamma in here has no dimension or no unit at all. The density rho of a gas also depends on the pressure, which in turn depends on the temperature. The speed of sound in an ideal gas is fundamentally a function of temperature T. Equation 2.6 represents this. Speed of the sound is square root of gamma times the R times the temperature over the molecular weight of the gas. R is the ideal gas constant. The temperature T is the absolute temperature expressed in kelvins, equal to the Celsius temperature plus the 273.15. Thus corresponds to 20 degrees Celsius equal to 293.15 Kelvin. And that's just 20 plus 273.15 to make it Kelvin. The quantity M is the molar mass or the molecular weight of the substance for which the gas is composed. And the gas constant R has the same value for all gases and is equal to 8.314 joule per mole K. And this is constant. Learning activity 2.3, speed of sound in air. Find the speed of sound in air at 20 degrees Celsius and find the range of wavelengths in air to which the human ear, which can hear frequencies in the range of 20 to 20,000 Hz, is sensitive. The mean molar mass of air, which is a mixture of mostly nitrogen and oxygen, is 28.8 times 10 to the minus 3 kilogram per mole. The ratio of heat capacities gamma is 1.40. We use equation 2.6 to find the sound speed from the gamma, the temperature, and the molar mass. And we use equation speed corresponding to its frequency and the wavelength to find the wavelengths corresponding to the frequency limits. Note that equation 2.6 temperature T must be expressed in kelvins and not Celsius. Now, temperature is 20 degrees Celsius and that is equivalent to 298 Kelvin. We find that the speed is equals to the square root of the ratio of heat capacities of the air, 1.40, the gas constant R, 8.314 joule per mole times Kelvin, and the temperature expressed in Kelvin, 293 Kelvin. That's 293 Kelvin. all over the molar mass given 28.8 times 10 minus 3 kilogram per mole. That will be cancelled, the K cancelled. Joule will be also cancelled and will be left with meters per second. Using this value of the speed, we use this in finding the wavelength of the speed of the sound or the sound. We find that at 20 degrees Celsius, the frequency 20 Hz correspond to 17 wavelength, 17 meter wavelength, and that 20,000 Hz correspond to 1.7 centimeter. We are now in the section 2.3, sound intensity. A useful way to describe the energy carried by a sound wave is through the wave intensity I, equal to the time average rate at which energy is transported per unit area across a surface perpendicular to the direction of propagation. Example is in this figure. We have a sensing equipment that it can sense the intensity of a sound. When we place this instrument near the source of the sound, it has very large intensity. Okay? That corresponds to 180. For example, 0 to 180. Now, when we place the instrument farther away from the source of the sound, it can sense a small value of intensity. Sound intensity may be measured in units of energy or work. Example are microjoules or 10 to the power of minus 6 joule per second per square centimeter, or in units of power as in microwatts, that is 10 to the minus 6 watt per square centimeter. The intensity of a sinusoidal wave is given by this equation 2.7. This expression shows why in a stereo system, a low-frequency woofer has to vibrate much larger amplitude than a high-frequency tweeter to produce the same sound intensity. So, equation 2.7 is 1/2 times the square root of density times bulk modulus times the angular frequency to the power of 2 and amplitude to the power of 2. It is usually more useful to express intensity in terms of the pressure amplitude Pmax. Expression or equation 2.8 represents this. This is another reason why it is usually more convenient to describe a sound wave in terms of pressure fluctuations and not displacement. If the sound source emits waves in all directions equally, the intensity decreases with increasing distance r from the source. According to the inverse square law, the intensity is proportional to 1 over r squared. Learning Activity 2.4 entitled Intensity of a Sound Wave in Air. Find the intensity of the sound wave in the Learning Activity 2.1 with Pmax equals 3 times 10 to the minus 2 Pascal. Assume the temperature is 20 degrees so that the density of air is 1.20 kilogram per meter cube. And the speed of sound V is 344 meters per second. Our target variable is the intensity of the sound wave. We are given the pressure amplitude Pmax as well as the density and the wave speed for the medium. We can determine the intensity from the given Pmax, density, and speed of the air, of the sound. Using equation 2.8, we can get 1.1 times 10 to the 6 watts per meter squared. Watts is just an equivalent of joules per second. Okay? This seems like a very low intensity, but it is well within the range of sound intensities encountered on a daily basis. A very loud sound wave at the threshold of pain has a pressure amplitude of about 30 Pascal and an intensity of about 1 watt per meter squared. Okay? Remember this, ha? The pressure amplitude of the faintest sound wave that can be heard is about 3 times 10 to the minus 5 Pascal, and the corresponding intensity is about 10 to the minus 12 watts per meter squared. Faintest means pinakamahina na naririnig ng ating tainga. So this intensity in here is naririnig pa ito or nasa-sense pa ito ng ating tainga. Learning Activity 2.5, Play It Loud. For an outdoor concert, we want the sound intensity to be 1 watt per meter squared at a distance of 20 meters from the speaker array. If the sound intensity is uniform in all directions, what is the required acoustic power output of the array? This example uses the definition of sound intensity as power per unit area. The total power in the target variable, the area in questions, it is a hemisphere centered on the speaker array. We assume that the speakers are on the ground and that none of the acoustic power is directed into the ground. So the acoustic power is uniform over a hemisphere 20 meter in radius. The surface area of this hemisphere is 1/2 of the surface area of the circle. And since the radius is 20 meters per second or 20 meter, we have 1/2 of that circle, and that is about 2,500 meters squared. Now, the required power is the product of this area and the intensity using the equation 2.9. Power is equals to intensity times the area. Thus, a 1 watt per meter squared times the area, 2,500 meters squared, has a power of 2,500 watt or 2.5 kilowatt. The electrical power input to the speaker would need to be considerably greater than 2.5 kilowatt because the speaker efficiency is not very high. The decibel scale. Because the ear is sensitive over a broad range of intensities, a logarithmic intensity scale is usually used. The sound intensity level beta of a sound wave is defined by this equation, equation 2.10a. Beta, or the decibel, is equals to, the sound intensity level beta is equals to 10 decibel times the log final intensity over initial intensity. This intensity in here is the intensity from the farthest part of the sound source, and the initial intensity in here is the nearest intensity from the sound source. And we can get also 2.10b. From this equation, we can get the intensity at the final equals initial intensity times 10 to the power of beta over 10 decibel. In this equation, initial intensity is a reference intensity chosen to be 10 to the minus 12 watts per meter squared. Approximately the threshold of human hearing at 1000 Hz. Okay? Recall the log means the logarithmic or the logarithm to base 10. This is the table 2.1, sound intensity levels from various sources. It has a respective value. For example, average whisperer. Ayan. It has a sound intensity level of 20 decibel and has a intensity of 10 to the minus 10 watts per meter squared. When we are In a busy street. Ayan, maingay na dyan. So, ang sound intensity level na meron dyan is 70 decibel. And the intensity is 10 to the minus 5. When we are in a living near an airport or near a military jet aircraft 30-meter away, sound intensity level is 140 and the intensity is 10 to the positive 2. That is why nakakabingi yung nakatira ka sa tabi ng airport. Okay? Yung intensity ng sound is very much larger. That is why yung mga nakatira doon usually nagkakaroon, not most, but nagkakaroon ng ear defect. Now, sound intensity levels are expressed in decibels, abbreviated dB. A decibel is 1/10 of a bell. It is a unit named for Alexander Graham Bell. He is the inventor of the telephone. The bell is conveniently large for most purposes, and the decibel is the usual unit of sound intensity level. If the intensity of a sound wave equals I/O, or the reference 10 to the minus 12 watt per meter squared, its sound intensity level is 0 decibel. An intensity of 1 watt per meter squared, it corresponds to a decibel of 120. And table 2.1 from the previous slide gives the sound intensity levels in decibels of some familiar sounds. Learning Activity 2.6, Temporary or Permanent Hearing Loss. A 10-minute exposure to 120 decibel sound will temporarily shift your threshold of hearing at 1000 Hz from 0 decibel up to 28 decibel. 10 years of exposure to 92 decibel sound will cause a permanent shift to 28 decibel. What sound intensities correspond to 28 decibel and 92 decibel? We are given two sound intensity levels. Okay? The 28 and the 92. Our target variables are the corresponding intensities, I. We solve this by using equation 2.10b to find the intensity that corresponds to each value of decibel sound intensity, beta. For execution, 2.10b for the intensity and beta is 28 decibel and 92 decibel. The exponents beta over 10 decibel is equals to 2.8 for the 28 decibel and 9.2 for the 92 decibel. So that equation 2.10b will be equal to this. Remember, the I/O is 10 to the minus 12 watt per meter squared. The reference intensity times 10 to the power of this one. And this one are equivalent to 2.8 and 9.2 respectively. So you just input the 2.8 for the 28 decibel and 9.2 for the 92 decibel. And each of the intensity will give us 6.3 times 10 to the minus 10 watt per meter squared and 1.6 times 10 to the minus 3 watt per meter squared. Thanks for watching and see you in the next part.